I'd like to talk to you about the frontiers of physics. When I say the frontiers of physics, you might think about cosmology, the large-scale structure of the universe. Why are we here? Why is there something and not nothing? Or you might think about quantum mechanics, the physics of the very small. What are the basic building blocks of the universe? But I don't want to talk about either of those subjects today. Instead, I want to talk about the remarkable things that can occur when we bring together countless number of interacting particles. If you take a single gold atom, it's not yellow and it's not shiny. But if you look at my wedding ring, it's both of those things. A single water molecule is not wet. A single DNA molecule is not alive. And a single neuron is not conscious. Shininess, wetness, life, and consciousness can only be understood by putting things together. This is the frontier of emergence that I'd like to talk to you about today. Physicists are simple people, and we like to think about the simplest possible examples. So I'm not going to explain the mysteries of life or consciousness. Instead, I want to talk about the physics of crystals. Here we can map a path from the basic building blocks of the universe to the remarkable properties that emerge in human-sized objects. I want to take you on a journey and show you some things that are stranger than we could possibly have imagined just from taking things apart. I'm a theoretical physicist, so my job is simple. I just start from our theory of everything and derive whatever complex phenomena I'm interested in. So I thought I'd start by writing down everything we know about the theory of everything. We have a problem. We don't have a theory of everything. We understand Einstein's theory of gravity, which is called general relativity, and we know about quantum mechanics. But we don't know how to combine the two theories, or even to use both theories at the same time. But that's okay. Gravity's not actually very important. I can demonstrate this for you if I just pick up my phone. Isn't this the most amazing science demonstration you've ever seen? Actually, although I pick up my phone far too often every day, what I've done is really amazing. I've used the electromagnetic forces in my puny muscles to overcome the gravitational pull of the entire planet. My muscles, or even a fridge magnet, can hold things up. We can only do that because gravity is pathetically weak. If we ignore gravity, then everything we've ever observed can be understood in terms of the standard model of particle physics. This model contains 17 particles, each described by 3 numbers: the electric charge, their mass, and their spin. It's been said that the first experiment was when a caveman picked up 2 rocks and banged them together to see what they were made of. And that experimental tradition is carried on by my colleagues in particle physics to this day. And it's been an incredibly successful tradition. First, they took an atom and smashed it to reveal that it was made of electrons and a nucleus. Then, they took the nucleus and smashed that to discover it was made of protons and neutrons. Finally, they split the proton and the neutron and found that they were made of quarks. But despite decades of trying, none of the 17 particles of the standard model have ever been split. So far as we can tell, they are point particles. That is, they're not made of anything smaller, and in fact, they have no size at all. However, most of these 17 particles are not important for what you see around you today. Everything you see around you today can be understood in terms of the electron, which we move around to give us electricity, the proton and the neutron, which form the nuclei of atoms and are responsible for the mass of objects in this room, and the photon, which is a particle of light and also carries the electric and magnetic forces. This is the theory of nearly everything. Just like our fundamental particles, the four basic building blocks of our theory of nearly everything are described by three numbers: their mass, their electric charge, and their spin. All of the matter particles, electrons, protons, and neutrons, are spin 1/2, whereas the photon is spin 1. What does this mean? Is something spinning? No. The electron is a point particle. It's not made of anything smaller, and it has no size at all. So there's nothing that could be spinning. Instead, it's better to think of each electron as a tiny bar magnet. The North Pole can be at the top, which physicists call spin up, or the South Pole can be at the top, which we call spin down. Magnetism occurs when the spins of electrons inside of a material align with one another. It's the combined magnetic force of the aligned electrons within a fridge magnet that allow it to overcome the gravitational pull of planet Earth. There are also less familiar types of magnet, quantum magnets. In the simplest quantum magnet, each electron aligns its spin in the opposite direction to the spins of its neighbors. This simple rule leads to absolutely remarkable properties. We can see these if we take a laser and kick an electron out of one of the atoms. This makes it easy for an electron from a neighboring atom to hop onto the first atom. We still have one atom with a little less charge than it started with, but we also have a little excess spin, two neighboring electrons with their spins pointing in the same direction. As more electrons hop through the crystal, the missing charge begins to propagate through the quantum magnet. Because we have two spins pointing in the same direction, it's easy for pairs of spins to flip. This allows the extra spin to move through the quantum magnet as well. Both processes happen at the same time, which means that the missing charge and the excess spin move independently through the crystal. If we do the quantum mechanics carefully, we find that two new particles have emerged: a spinon, which has spin but no charge, and a holon, which has charge but no spin. Remember that, as a species, we have never split a single electron. But by bringing many electrons together inside of a quantum magnet, we've split the electron into a spinon and a holon. The remarkable physics I'm telling you about happens in crystals, which are just periodic arrangements of atoms or molecules. This periodic pattern is hard to change, and that makes crystals rigid. This video shows a long, thin molecular crystal grown by my friend and colleague, Jack Clegg. He and co-workers discovered that as you bend this crystal, the periodic pattern does not change. The crystal retains its crystallinity even as it's bent. In fact, these crystals are so flexible, you can even try them in a knot without destroying the crystallinity. We discovered that at low temperatures, these molecular crystals become quantum magnets. High temperatures destroy magnetism. For example, iron is not magnetic above 770 degrees Celsius. The same is true for quantum magnets. Yet, when you bend these molecular crystals, the temperature at which they become quantum magnets increases 1,000,000,000,000,000,000 times. I don't know about you, but I find it hard to understand what it means for one thing to be 1,000,000,000,000,000,000 times bigger than something else. So I started thinking about the actual sizes of objects. Let's start with something pretty small. A fly is about 1,000,000 times smaller than a suburb. A suburb is about 1,000,000 times smaller than the sun. The sun is about 1,000,000 times smaller than the Oort cloud. the farthest reaches of our solar system, and the Oort cloud is about 1 million times smaller than the Milky Way, the galaxy that we call home. So a fly is 1 million, 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 million times smaller than the Milky Way. And that's how much we can increase the temperatures at which molecular crystals become quantum magnets just by bending them. Our theory of nearly everything has some profound unsolved questions. For example, in the 19th century, we learned that electricity and magnetism are two sides of the same coin, which is why we now talk about electromagnetism. We've also seen that our 4 basic building blocks of our theory of nearly everything are described by 3 numbers: their spin, their mass, and their electric charge. But if electricity and magnetism are so similar, why don't they also have a magnetic charge? In decades of searching, physicists have never managed to observe an isolated magnetic charge in the vacuum. You might have tried an experiment as a child to look for magnetic charges yourself. If you take a bar magnet and break it in 2, you don't find a north pole and a south pole, which would be individual magnetic charges. Instead, you get 2 smaller bar magnets, each with a north pole and a south pole. This is a picture of a type of quantum magnet called a spin ice. It obeys a simple rule known as the ice rule. Each of the down triangles has 2 spins pointing into it and 1 spin pointing out. Each of the up triangles has 2 spins pointing out of it and 1 spin pointing in. If we flip the spin of one electron, which we can do by hitting it with a beam of neutrons, this creates a south pole in one triangle and a north pole in another. The spin ice can try and repair the ice rules by flipping 2 different spins, but all this does is to move the 2 poles further apart. As more spins flip, the north pole and the south pole begin to move independently through the crystal. That is, we have 2 particles moving independently, each with a magnetic charge. Now the south pole has reached the edge of the crystal. By flipping 1 more spin, the spin ice can repair the ice rule in that corner of the crystal, and we're left with a single particle carrying a magnetic charge. That is, we have made a magnetic charge not by tearing things apart, but by putting things together. I hope that I've shared with you just a little of the wonder of emergence. We've seen that in quantum magnets, we can split the electron, a particle that's never been split in the vacuum. We've discovered that by bending molecular crystals, we can increase the temperature at which they become quantum magnets 1 million, 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 million times. And we've found magnetic charges, not by tearing things apart, but by putting them together. So the next time you take a swim in the sea, I'd like you to remember that its wetness emerges from the interactions between countless water molecules. And recall that in crystals, even stranger things happen because of the interactions between countless electrons. I'd like to leave you with a quote from Arthur Eddington, the great astronomer whose observations helped confirm Einstein's theory of general relativity. He said, "We used to think that if we knew 1, we knew 2, because 1 and 1 are 2. We are finding that we must learn a great deal more about and."